What is nano? A man's beard grows 5 nanometers every second. Oh, suffice it to say, a nanometer is very, very small. Despite its size, you can see the effects of things happening at the nanoscale all around you. They give the sunset its red color, allow birds to navigate, and help geckos stick to trees. But it's only recently that we've actually been able to see down to the nanoscale. This is nano-you. We humans are strange creatures, aren't we, if we're honest? We like to measure things. Earth's tallest mountains are over 8,000 meters tall. A football pitch is around 100 meters. I myself am about 2 meters when I'm standing up, in shoes. Good afternoon. Ants are a few millimeters long. Skin cells about 30 micrometers. We can't see things this small. A bacterium is about 2 micrometers. Smaller still are viruses and phages. And so we go down to DNA, our molecular blueprints. DNA is 2 billionths of a meter in diameter, or more conveniently, 2 nanometers, the units that we used to measure the building blocks of everything. Welcome to the nanoscale. To explore the nanoscale, we use very powerful machines called electron microscopes.
Today we're going to look at 2 things that you may have seen before. We're going to look at a fly and a coin. So this is the Z on the coin. This is the fly's wing. And who would have thought that it would have had all these little hairs sticking out from it? The tip of each of those hairs is only about 600 or 700 nanometers in diameter.
When we use electron microscopes, we explore new and alien landscapes. It's a strange new world down there. The nano world isn't just unusual looking, things behave differently there too. One reason for this is surface area. If you take a cube and lay the surface flat, you can see how much of that cube can react with the outside world. If you divide the same cube into 8 little cubes, the surface area is twice as big. If you keep making smaller cubes, the surface area becomes immense. More surface means more area for reactions. This is why powdered sugar dissolves faster than sugar cubes. Big lumps of aluminium are not very reactive, but nanoparticles of aluminium are so reactive they can be used in rocket fuel.
Another way you can show this is with flour, because flour doesn't burn very easily when it's in a pile, because it hasn't got enough surface area. But if you mix it with a lot of air, then something quite different happens.
Light also behaves differently as you head down to the nanoscale. White light contains all colors. When particles get really small, they start to bounce only certain colors back, so you see them as those colors. As gold gets smaller, it stops looking gold and instead reflects red, purple, blue, and finally becomes invisible when it's too small to reflect any colors of light that you can see. These strange properties of light can be very useful. Welcome to nature's nano.
I've always wondered how butterflies and beetles can make these strong iridescent colors. So if we take a butterfly wing and we put it under a microscope, we see thousands and thousands of small little bright blue scales. Each of these scales is covered by little ridges running across a scale. Each of these little ridges, if you cut right through them, look like a Christmas tree.
This structure is finely tuned to reflect only the blue part of light, so the butterfly appears bright blue.
If we just replace the air in this nanostructure with a bit of liquid, you'll see that it changes color from bright blue to bright green.
It fills in the gaps around the nanostructure and makes it better at reflecting green light. When the liquid evaporates, it returns to reflecting blue. Please, don't squirt butterflies. Life has spent 3.8 billion years finding clever ways to use the nanoscale. Now we can understand nature's nano secrets. We can use them for ourselves. Many tropical plants have leaves where water just runs off. This keeps them clean. If we look at the nanoscale, we can see tiny structures which stop the water from sticking. By copying these structures, we can make our own water-repellent surfaces. Some that even honey doesn't stick to.
Ants have really cool feet. They can stick upside down to surfaces, holding up to 100 times their own weight, without falling down. If we look closely, we see tiny little pads on their feet that help them to stick.
By investigating the microstructure of insects' feet, we can design surfaces hard for them to climb. Bad luck for cockroaches. Pitcher plants eat insects that slip into them, but they don't work unless all of their rim is covered in water. To make sure they're as slippery as possible, they have a nano trick up their sleeves.
You can see how the water spreads, even upwards against the gravity. If we look at them, we see that they have lots of grooves running across their rim. And in between these grooves, if we look on a nanoscale, there are even smaller grooves.
This is called a superhydrophilic surface, which means that the surface likes the water and pulls it across itself. Once the water is spread thinly across these micro and nano grooves, they become very slippery, and it's goodbye ants, hello pitcher plant dinner. Hydrophilic surfaces have lots of uses, but one particularly excellent one is in a new water filter. This can filter even the tiniest bugs from dirty water, making it safe to drink. Even really dirty water. Looking around the natural world is a great way to pick up ideas for things to make ourselves. But with nanotechnology, we can make new structures that nature has never even tried. Down at the nanoscale, things are gloopy and there's lots of friction. This means particles stick together really easily, and if this happens again and again, new and complicated structures can be formed. This is called self-organization. Scientists have been carefully experimenting with different conditions to see what sorts of new nanostructures they can create. The results are astonishing.
Here are some samples that I made under various conditions, but when we zoom in on the nanoscale, we can see that they are extremely different. So these ones remind me of the Eiffel Tower. They're really quite beautiful, these hexagons all stacked on top of each other, like pyramids. We can also make other materials, such as really thin wires, ones that look like pancakes, or ones that look like flowers.
All these new structures have different properties. Soon they'll be changing the way we live. From solar panels that we spray onto our roofs,